Okay, this is the Machine Learning Foundations course, end of course project in the AI product management specialization from Coursera as delivered by Duke University. The project objective was essentially to build and train a model to predict the electrical energy output of a combined cycle power plant on an hourly basis. And there were 4 key elements: determine the features and algorithms to use, determine a data splitting and validation strategy, validate 2 or more models with differing variables, and then evaluate model performance and provide an end of course review, which is what this is. From a features and algorithms perspective, determine what type of machine learning approach. So the modeling task that I'd identified as part of this was to predict a numerical value, with the net hourly electrical energy output being the prediction itself. This lends itself to a parametric algorithm since it is numerical, a nonlinear regression based on my review of the materials and the data that was included, in a supervised learning approach. The output metric that I identified was mean absolute error. Since we are taking a look at this from an hourly basis, I estimated that it would be more important to be accurate most of the time, with outliers not really having a significant impact, as opposed to outliers having a major impact by squaring that algorithm in order to determine the error. And then the features themselves, there were 5 features included in the data set that was provided. There was about 10,000 records in that data set, so relatively small. Ambient temperature looked to be the most relevant, and along with ambient pressure, relative humidity, exhaust vacuum, and again, the net hourly electrical energy output was our target prediction. Model building, comparing at least 2 different models and selecting the one that provides the best performance. The validation type that I included here was cross-validation using K5 folds. I felt like this provided the best opportunity for the data given the small data set. I actually decided to use Google Cloud's Vertex AI, which is the auto ML feature that was one of the potential approaches defined in the course. It was my first time using it, so I wanted to get a better handle on how that worked and how that could create, build, train, and test models. So use that, and we'll see some outputs of that in a moment. The model types, I chose 3 different model types with different variables. I removed the ambient temperature, seeing as how it was the most important variable or feature that was included, to see what that would do. I ran an alternative validation split, a 95-5, as opposed to an 80-10-10. 80-10-10 was run on the 2 here, the top and the bottom bullets. And then I included the ambient temperature and ran it at an 80-10-10 as well, just to show a difference between the different variables when I included that feature specifically and when I excluded it, along with the different splits, validation splits. And then finally, model interpretation. So you'll note here on the right-hand side, the first run, the training 1, version 1, had the mean absolute error of 3.9. This is the one where I excluded the ambient temperature, and you can see that orange line is missing in the AT section on the feature importance on the left-hand side. That actually resulted in the worst error or predictability or ability to predict of all of them. Then in the second run, the blue lines, I included the ambient temperature back in, and this is the one that I changed the validation to be a 95-5. And that actually created the best MAE for all of them at a 2.344. And then just for baseline purposes, to go back and just test that validation again, I went back and ran version 3 or run 3 version 1 with a 2.5 MAE. What I did here was I included the ambient temperature again, but I ran it at an 80-10-10 validation split just to see how the different validation split would impact the results. So based on this training that I've run with the different models, it looked like including the larger training set of the 90% data for training, 5% for validation, 5% for testing, resulted in the best result, while also including ambient temperature. With the test run 3, which included ambient temperature but used the 80-10-10 split, was slightly behind that.